Everyone, and welcome back to Organic Chemistry on YouTube. Today, we're going to be talking about E1 reactions, starting with alkyl halides and the implications of this reaction with regards to stereochemistry. Some of the most important things you should know about E1 reactions is that the reaction has unimolecular kinetics. The reaction rate depends on the substrates alone. This reaction is generally promoted by using weak bases. Strong bases favor E2 reactions. Within the reaction, there's a carbocation intermediate that's formed, and this intermediate leads to the possibility of different stereoisomers. In this case, because we're doing an elimination reaction, the product will be an alkene. So if the reaction can form cis and trans isomers, it will. And finally, you might want to watch out for hydride shifts, which are also possible with these reactions, just like in SN1 reactions, where the first step is that the leaving group leaves. Let's turn to one sample reaction and do a mechanism. This involves the reaction of a secondary alkyl bromide in the presence of methanol and heat. When this reaction proceeds, you get a mixture of products, cis and trans butene, as well as 1-butene. So let's work out the reaction mechanism and try and understand how you can arrive at these different products using the arrow pushing or curly arrow based mechanisms. So the first step of any one of these E1 or SN1 reactions is that the leaving group leaves. So I'm going to show the electrons from the carbon-bromine bonds leaving, being kicked onto the bromine leaving group, a carbocation intermediate. And this is a secondary carbocation. This secondary carbocation will then have the possibility of reacting with methanol, where methanol acts as a base. What I'm going to do is just highlight these different types of hydrogens or protons that can be deprotonated in blue. So first of all, there are these methyl hydrogens, yellow hydrogens over here. The base we're going to put in red, and the basic part of this molecule is the lone pair on oxygen. So taking that lone pair, making a bond with the hydrogen, the blue hydrogen over here, we're going to take that hydrogen away to deprotonate it, and we're going to move the electrons from the carbon-hydrogen bond onto the carbon framework to make a pi bond. So this is going to make an alkene. We could also deprotonate one of these yellow hydrogens, which I'll also do in red, just as using a separate methanol molecule, to be clear. Again, I'm going to deprotonate the hydrogen, move the electrons from the carbon-hydrogen bonds onto the carbon framework, and make the following molecule. Okay, and then here we have the trans 2-butene, which is here. Now we're out of different hydrogens to deprotonate, right? We only have the yellow ones and the blue ones. We need to be able to also arrive at this cis 2-butene. So the way that this cis 2-butene reaction forms is through realizing that this molecule has different conformers, and we can deprotonate the same hydrogens, but in a different conformation. Remember that you can rotate around sigma bonds, but not pi bonds. So when the molecule is in this conformation, we'll still deprotonate one of these hydrogens and arrive at the cis 2-butene, which I'll show in blue. Okay, the mechanism is virtually the same. A key piece of this is that when you have these carbocation intermediates, you can rotate around them and lead to a mixture of stereoisomers. Showing an example now that just covers the possibility of a hydride transfer in an E1 mechanism, we again have a secondary alkyl bromide. And in the first step of the reaction, just like all E1 reactions, the leaving group leaves, and we end up at the secondary carbocation. Recognizing that you have a hydride here in green that could transfer to that carbocation will lead to a tertiary carbocation, then a secondary carbocation, so the shift will happen. And now you have two different types of hydrogens, again, that can be deprotonated. So methanol can come and deprotonate either of these. There's this product, and then if you deprotonate at one of these methyl hydrogens, so which one of these is the favored product between these two red ones, A or B? Take a second, try that on your own, and then press play again after you've attempted the question. A is the Zaitsev product, and it has the more substituted alkene, which we know is more favorable. So this ends up being the more favored product. With that, thanks very much. This has been Organic Chemistry in 5 minutes or less.